Chapter 8 Principle Stress Homework Solutions 8.1 We want you to determine the principal planes and the principal stresses for the plane stress from superposition or simple addition of two states of stress. So you are having two states of plane stress, one on the left, one on the right. And we want to know, after you do the so-called superposition or addition between these two stress states, and you get something like this. And for the combined stress state, we want to know the principal planes and the principal stress. Okay? So this is what we learned in chapter 8. And the hint, of course, would be you can do this either by rotating or transforming the stress state on the right. For example, rotate it clockwise 45 degrees to be aligned with the stress state on the left, and then you can do superposition or linear addition. And once you have the combined stress state, you can get the what we using Mohr circle, you can get the principal planes and the principal stress. Okay, you can, for the stress state on the right, you can rotate it in real geometry or real space clockwise 45 degree, which means if you're going to use Mohr circle method, you have to rotate a Mohr circle by 45 times 2, 90 degree, to find the stress state in the corresponding plane on Mohr circle. Okay. So how do we do this? We copied the stress state on the right, and we said we are going to transform or rotate the stress state on the right to the direction of interest. Rotate it, let's say clockwise 45 degree, so that it aligns to something like this. But how do we do this? Starting from the stress state on the this one, assuming this is our x prime direction, this is our y prime direction. So based on this, we would know the coordinates for two related points on Mohr circle. So starting from this, we would know the coordinates for two related points on the Mohr circle. So for the x prime point, it would be 12, 0. Why 0? Because there's no shearing stress in this x prime plane. For the y prime point, it would be, because it's going in, it would be -8 megapascal, 0, because there's no shearing stress in this plane. So x prime would be 12, 0. Y prime would be -8 by negative, because it's pressing in, compressive stress, 0. Okay, so we know the coordinates for two related points on the Mohr circle just based on this. And these are two related points. We said when you connect x prime and y prime, it should go through the center for the Mohr circle, and we also know the center of the Mohr circle should be on the horizontal axis or the normal stress axis. So where is the center? So this is 12, this is -8, and the average is 12 plus -8, which is 4 divided by 2. It will be 2, and of course the vertical would be 0. So the center C would be at 2, 0, and the radius would be from x prime to C would just be 10. Okay, the radius for this Mohr circle would be 10. And then how do we rotate? We said from x prime rotate to the horizontal x, you would rotate in real space by 45 degrees, which means on Mohr circle, you have to go from x prime, rotate in the same fashion 45 times, but 45 times 2 theta p. Okay, which is Uh, here, and here you would find the x, and the 90 degree you will find the x. And because of 90 degree, where is x? It of course would be 2, comma, and it's rotate clockwise, so the vertical would be minus radius or minus 10. And similarly for y we said, okay, from y prime you rotate clockwise by 45 degree, which means in more circle you go from y prime rotate clockwise by 45 times 2, 90 to find the y point, and it's directly on top of C because it's 90 degree, and of course the horizontal coordinate would be 2, and the vertical coordinate would just be the radius, which is 10. Okay, so now we know the x and the y point, x and y point, and the x point on more circle represent the horizontal axis, and of course this is 2, so here we should have 2, and the shearing stress, the minus 10, the shearing stress should be 10, but which direction? It's minus 10, minus 10. Remember the Mohr circle convention. If the shearing stress is trying to rotate this local unit clockwise, we call it positive, but because it's negative, so we draw this up like that. It's trying to rotate the unit counterclockwise. Similarly, for the y direction, it's 2, 10. 2 is positive tensile, so 2 go here, and then the shearing stress is 10, but which direction? It's positive, so it should be trying to rotate this local unit clockwise, so we draw it this way. So now you see tensile stress along 2 megapascal along x-axis, tensile stress 2 megapascal along y-axis, and shearing stress 10 coming together here. Okay, so this would be the transformed or rotated stress that is equivalent to the original stress state that we draw here. After we did the transformation or rotation for the stress state on the right, now we combine, we do the superposition for the two stress states. This is the original stress state on the left, this is the stress state on the right, but after rotation or after transformation. Now they are aligned. Now we can do the superposition or simple linear addition. For horizontal x direction, it will be 10 megapascal for tensile, 2 megapascal for tensile. The combined will be 12 megapascal for tensile. For the vertical y direction, it is 6 megapascal for compression, 2 megapascal for tension. So combined would be 6 minus 2, 4 megapascal for compression, going in for compression. Then for shearing stress, for the x-plane, the plane perpendicular to the x-axis, we have 4 megapascal rotating clockwise, but 10 megapascal rotating counterclockwise. So the net would be 6 megapascal rotating counterclockwise. For the y-plane, the plane that is perpendicular to the y-axis, we have 4 rotating counterclockwise, 10 rotating clockwise. So the net would be 6, but also rotating clockwise. Okay, so this is our combined stress state. 12 tensile along x, 4 compression along y, and 6 of shearing stress going this way, going this way. Finally, we have this combined stress state, the stress state from the superposition of the original two stress states, one on the left, one on the right. The right one we did rotation or transformation, and then we did the superposition or addition for the two to get this stress state. The last step is to determine the principal axis and the principal stresses for the combined stress state. Okay, so this is our combined stress state. If we're going to use Mohr circle method, based on this, we would have the coordinates for two related points. Coordinates for two related points. Horizontal axis or x direction, we have the capital X point, and the coordinate are 12 tensile, so 12 comma, and 6 for shearing stress, and it is trying to rotate the local unit counterclockwise. So based on Mohr circle sign convention, it will be -6. Okay, the x coordinate are 12 comma minus 6. The y coordinate would be, okay, 4 for normal stress but going in, so -4 comma, and then the shearing stress also 6, and it's trying to rotate the unit clockwise, so +6. Okay, so we have the two coordinate for two related points. X is 12 minus 6, 12 minus 6, y would be -4 comma 6. So we know the coordinate for two related points are Mohr circle, and these are again related points. When you connect them, you should go through the center, and the center should be on the horizontal axis. So where is the center? So this is 12, this is -4. The average would be 12 plus -4 is 8 divided by 2. The average would be 4 comma, and the vertical of course would be 0. So the center C would be at 4 comma 0, and the distance from here to here would be 12 minus 4 would be 8 for horizontal. The vertical would be 6. So the radius for this Mohr circle would be 10 megapascal. Okay, 10 megapascal. So to determine the principal stress, the location would be at center plus radius. It would be 4 megapascal plus a radius, which is 10. The total would be 14 megapascal. That will be the coordinate for A point, the maximum normal stress, 14 comma 0. And what is the angle? Where is it? So you see on Mohr circle, from X to reach A, you have to rotate counterclockwise for an angle by 2 theta p. But what is this 2 theta p? It can be get by A tangent of opposite to side. Opposite would be 6, side would be 8. So A tangent of 6 over 8, which is 0.643 radian, or 36.8 degree. So on Mohr circle, from capital X to A, you rotate 36.8 degree, which means in real space or in real geometry, from horizontal X, you also rotate counterclockwise, but by half of that angle, which is 0.5 times the 36.8 is 18.4 degree. Rotating in real space 18.4 degree counterclockwise from X, from horizontal X, you would find the maximum normal stress, which is tensile stress, because it's positive. Similarly, to find the minimum stress on Mohr circle. To find the minimum stress on Mohr circle, you can the absolute value would be center minus radius, which would be 4 for center, minus radius, which is 10, it would be -6 megapascal. So the B coordinate, the minimum normal stress or the maximum compressive stress would be at B, which is -6 comma 0. And where is it? You can find it going from Y direction, rotating also on Mohr circle counterclockwise by the same 36.8 degree. So which means in real space to find the Y, you or to find the B, you would start from Y and rotate same fashion counterclockwise, but by half of that angle, which is 18.4 degree, rotating counterclockwise from Y, rotating counterclockwise by also 18.4 degree to find the minimum normal, also called the maximum compressive stress. Okay, and this completes this problem. We find the principal stress, and the principal axis where it is. It is the maximum tensile. It would be at 18.4 degree, rotating counterclockwise from the horizontal axis. The minimum normal stress or the maximum compressive stress, you would start from Y and rotating also counterclockwise by 18.4 degree to find the minimum normal or maximum compressive stress. Homework 8.2. A 100 pound of vertical force is applied at point G of the very edge of a gear DG with a diameter 2 inches, connected to the solid 0.5-inch diameter shaft DE. So we have a shaft DE, we have a gear DG, and at the edge of this DG gear, we are applying a 100-pound vertical force. Okay? And we want you to calculate the principal stresses and the maximum shearing stress at point K. Located on the top surface. This is at the side vertically down. The K is at the top of the shaft, 10 inches away from the G end or the D end. Okay, so this is our problem. The hint would be the local stress state would be the superposition of the stress state caused by bending due to this vertical downforce, and because it's off center, it's going to cause torsion. Okay, the local stress state would be the superposition for two effects. One is due to bending for the shaft, one is due to torsion or torque on the shaft. Okay, so how do we do this problem? First, let's calculate what's for the torque part, the net torque, trying to twist the shaft, the net torque would be force times the off-center distance, which is D1 divided by 2. So 100 pound times 2 inch, but divided by 2 because 2 inch is the diameter, radius would be 1 inch for the gear. Okay, so the torque would be 100 pound-inch. That's the torque part. The shearing stress at K due to torque alone, T alone, would be tau is from chapter 3, Tc over J. T is the net internal torque, C is the maximum dimension or radius for the shaft, J is the moment of inertia, circular, for this shaft. Okay, so T we said is 100 pound-inch, C for the shaft diameter is 0.5 inch diameter, so radius is 0.25 inch, and J for the solid shaft will be half pi, radius to the power of 4, and radius is 0.25 inch. And you plug in the number, you got 4076 psi. That is the local shearing stress due to the torque alone. So previously we calculated the shearing stress component. Now let's consider the normal stress due to bending moment. The bending moment at K point due to displacement of the vertical force. The moment would be force times this displacement. The force we set is 100 pounds. The displacement from K to G along this axis would be 10 inch. So the total bending moment would be 1,000 pound inch. So the resulting normal stress at the top surface K would just be from chapter 4 for pure bending, MC over I. M is 1,000 pound inch, C radius 0.5 inch divided by 2.25 inch, and I for this cylindrical shaped solid shaft would be 1/4 pi radius to the power of 4. Okay, and the normal stress would be 81,528 psi. Okay, so that will be the normal stress along the longitudinal axis due to the bending effect by itself. Okay, so now we have shearing stress, we have bending stress. In terms of total stress state at K, it has two contributions. One is from bending moment, and along the x-axis. The other one is shearing component due to the torsion, torque T. So the resulting stress state, if this is our x, this is our y, this is our z. So the resulting stress state I plotted up here. The normal tensile stress 81,528 psi along horizontal x-axis, and there's no normal stress along at K surface along y direction, so the sigma y would be 0, sigma x is what we said, and the tau xy would be from the torque calculation, from torsion calculation, 4,076 psi, and I draw it this way. I'm considering the local unit here and looking from the front surface, from the E direction. So this is our local stress state, sigma x, sigma y, and the tau xy. Okay, and of course, once you have this, you can use either Mohr circle or the equation set. Once we have the three stress component, if we're using the Mohr circle, the average would be just the sigma x plus sigma y divided by 2, and the sigma y is 0, sigma x is 81,528. So the average normal stress for the Mohr circle would be 4.08 times 10 to the power of 4 psi. Is essentially to reduce the number of significant digits. The radius for the Mohr circle would be the difference divided by 2 squared plus the shearing stress squared. Take the whole thing square root, and it come out to be 4.10 times 10 to the power of 4 psi. So that's a radius, and then the principal stresses would be, for A point, the maximum would be average plus radius. It comes up to be 8.18 times 10 to the power of 4 psi. The minimum normal would be average minus radius, comes up to be minus 0.02 times 10 to the power of 4 psi, very close to 0. And the maximum shearing would be, because one is positive, one is negative, the maximum shearing in 3 dimensions would just be the radius for this circle, and it is 4.10 times 10 to the power of 4 psi. Okay, and that solved the problem. You have the off-centered vertical force at the very edge. It causes bending, it causes torsion, and bending gives normal stress, torsion gives shearing stress, and you combine, we have the local stress state, and using Mohr circle or the equation set, you can get the principal stress and shearing stress.